All right, so I am going to present question 1. So in question 1, we are comparing two different reactions, reaction A and reaction B. So what we're given is that reaction A is half complete at 20 minutes and 75% complete after an additional 10 minutes. And reaction B is also half complete after 20 minutes, but only 2/3 complete after 40 minutes. So part A asks, what are the order of reactions for both A and B? First of all, we can graph these reactions better to understand them, which is what I've done here. And specifically, we can graph the fraction of initial reactant remaining as a function of time. And this would help us understand better how the rate of reaction depends on the amount of reactant present at a given time. So for reaction A, it is, as we are given, it is half complete after 20 minutes, and it is 75% complete after an additional 10 minutes, which means that 25% of the initial reactant concentration is present at the 30-minute time point. So from this, we can see that reaction A proceeds with a constant rate. So that is that the total amount of reactant that decreases at each time interval is constant. And so the reaction rate is independent of the concentration of reactant that's present at any given time. So which order reaction do we know that is independent of reactant concentration? Well, we know that this is a zero order reaction, because a zero order reaction is independent of reactant concentration. So reaction A is a zero order reaction. Now we can do the same thing for reaction B. So reaction B is also half complete at the 20-minute time point, but at the 40-minute mark, it is only 2/3 complete. And that means that only 1/3 of the initial concentration is left. So that means that there is a greater decrease in reaction B between the 0-minute and 20-minute time point than between 20 minutes and 40 minutes. And so that means that over time, the reaction seems to slow down. So from this graph, we can see that the rate of reaction B, first of all, does depend on the reactant concentration at a given time. So we know that reaction B is not a zero order reaction. Now we can determine whether it's a first order or second order reaction really simply through the half-life. So to reiterate the definition of half-life, half-life is the time required to convert half of the initial reactant concentration to products. So first order reactions have a constant half-life, and the half-life of a first order reaction is given by this equation. Half-life T1/2 is equal to ln2 over K, where K is the rate constant. And this means that in a first order reaction, the time required to go from 100% to 50% of reactants is the same as the amount of time required to go from 50% to 25%. So for second order reactions, on the other hand, T1/2, the half-life is given by this equation. T1/2 is equal to 1 over the initial reactant concentration times K. So half-life for a second order reaction is inversely proportional to the initial reactant concentration, A0. And so this means that as the reaction proceeds and as the reactant concentration decreases, that means that half-life increases over time. And so this is what we see in reaction B. We can see that through this graph, the half-life decreases as the reaction proceeds, or sorry, the half-life increases as the reaction proceeds, which means that the rate of the reaction decreases. So we can test to make sure that reaction B is a second order reaction by plugging in the data points that were given into the half-life equation. So for example, from the first time point, we can determine that for at T equals 0, the half-life is 20 minutes, since it takes 20 minutes to get to half of the reactant concentration. So we can calculate for this point, 20 minutes, the half-life, is equal to 1 over the initial reactant concentration, which we can just say is some arbitrary concentration, and an easy one in this case would be 1 molar. So we can say 1 molar times K. And so then we can solve for K. And in this case, we get K is equal to 0.05 per molar per minute. So now that we have K for reaction B, we can plug K in to the rate equation that we would expect for a second order reaction. And we can determine what is the expected concentration at T equals 40 that we would expect. And is this concentration, does this match up with what we observe at time 40 or at 40 minutes? So, so we can plug K in to the rate equation, and the rate equation for a second order reaction is A is equal to A naught over 1 plus A naught times K times T. And this is a concentration of A at 40 minutes that we're trying to calculate, given that the initial reactant concentration is 1 molar. This was also 1 molar, as we have determined an arbitrary concentration. And then K would be 0.05 per molar per minute. And we're trying to determine for the 40-minute time point. So T is 40 minutes. And so then we can solve for the concentration that we expect then at 40 minutes, and that is equal to what we get from calculating this. We get that to be equal to 1/3 molar, and that is equal to 1/3 of the initial concentration, 1 molar. And so we can see that that is what happens. That is what we observe in this reaction, that after 40 minutes, 1/3 of the initial concentration is remaining. So from that, we can determine that reaction B is in fact a second order reaction. So reaction B is second order. Now, part B asks, how long will each reaction take to reach 90% completion? So 90% completion means that 90% of the reactants have been converted into products. And so 10% of the initial reactant is still remaining. So for reaction A, we know that it's a zero order reaction. So we can plug in one of the data points again that we're given into the zero order rate equation. And the zero order rate equation is concentration of A equal to A naught minus KT. And so here we can use, for example, the 20-minute time point at which 0.5 of the initial concentration is remaining. So if we again say that the initial concentration is 1 molar, that means that 0.5 molar remaining. So 0.5 is equal to 1 minus K, and then T would be the 20-minute time point. So then we can solve for this, and what we get is that K is equal to 0.5 molar over 20 minutes, which is equal to 0.025 molar per minute. So that is the value of K that we get. So now we need to use this rate constant in the same equation, to determine the time it takes for 10% of the reactant to remain. So we can say that 0.1, so 10% of the initial reactant, is equal to 1 minus K, so 0.025 molar per minute times T. And then we just solve for T. That will tell us how long it takes reaction A to reach 90% completion. Now for reaction B, we can do the same thing. Since we know that it's a second order rate equation, we know that the rate equation is A equals A naught over 1 plus A naught KT. So we have already solved for K from part A, so we can just plug that in. And so here we have 0.1 or 0.1 molar. Here's also molar, this is molar, is equal to initial concentration, that's 1 molar. K, we know from up here that it is 0.05 per molar per minute. And then all we need to do is solve for T, and that will tell us how long it takes reaction B to reach 90% completion.